Let us now discuss some questions. Now the first question, that is addition of HBr in presence of peroxide. Now such additions occur by anti-Markovnik's rule, so that negative part of the addendum bonds to the unsaturated carbon connected to the largest number of H atoms. So that bromine should connect to this carbon and hydrogen to this carbon. Now, discussion of mechanism in brief. The peroxide ROR undergoes homolysis to give RO radical. Now the dot represents radical center. Now a radical reacting with a molecule HBr producing another radical and another molecule. HBr undergoes homolysis, H radical is created. This H radical combines with the O radical center producing ROH and Br radical. Now this Br radical attacks this molecule, and this molecule may be called three phenyl propane. So it is 3-phenyl propene. Now the pi bond undergoes homolysis in this direction, so we get an orbital with a free electron here, and again an orbital with an unpaired electron here. Now this unpaired orbital combines with the unpaired orbital of bromine to form a sigma bond between CS2 and Br. Now this is a secondary radical. Now this radical can be stabilized by hyperconjugation involving these two CH bonds and these two CH bonds. So again this radical combining with another molecule HBr that undergoes homolysis, we get H radical which combines with this radical center to form a CH sigma bond and a Br radical, and this Br radical will further react with the 3-phenyl propene, so it is called a chain reaction. Now the other product is also possible. Then that will be a product where Br is getting connected to the carbon bearing connected to lower number of H atoms, but that will be formed to a smaller extent. So the major product will be this one. Now then another example, it is simple and there is no peroxide, so the addition is according to Markovnik's rule. The negative part of the addendum, HCl is the addendum. The negative part, that is chlorine, gets connected to, bonded to the carbon, unsaturated carbon containing the least number of H atoms, here only one H. So chlorine connects here and H connects to this unsaturated carbon containing greater number of H atoms. So the molecule is two chloro 2-chlorobutane. Now there is another question, why concentrated sulfuric acid is not used during the reaction of alcohols with the potassium iodide. Now concentrated sulfuric acid is an oxidizing acid. With potassium iodide, sulfuric acid reacts to give KHSO4 and HI, reaction number 1. Then H2SO4 will give H2O, SO2 and nascent oxygen. Now this nascent oxygen will react with HI according to this equation, and H2O and I2 are formed. So HI will not be available for reaction with the KROH. So the reaction ROH plus HI is prevented. Hence sulfuric acid concentrated cannot be used during the reaction of alcohols with Ki. Now sulfuric acid is an oxidizing agent. At the same time, HI, that is hydroiodic acid, is a reducing agent also. Now write the structures of different dihalo derivatives of propane. That is another question. Now there you write propane molecule and place a mirror along the dotted line shown in the figure. Now suppose we are placing a mirror like this. This CH3 becomes the image of this CH3. So these CH3 groups are similarly placed, we say. Hence we use the CH3 groups by tick marks because they are similarly placed. And this CH2 is different. Now we can connect the two chlorine atoms to this carbon or to this carbon. Both are the same. So connecting two carbon atoms to this CH3 group, we get Cl2CH, CH2CH3, and that is 1,1-dichloropropane. Now again, this is a different carbon. It's a secondary carbon. It's different from these two primary carbons. So the two chlorine atoms may be connected to this carbon. We get 2,2-dichloropropane. Then we can select two carbon atoms for connection of chlorine. So connect one chlorine to this CH3 and the other chlorine to this CH2. We get 1,2-dichloropropane. Then a last isomer is there. You connect one chlorine here and one chlorine here. We get 1,3-dichloropropane. So these are the various isomers possible for the dihalogen derivative of propane. Now another question, among the isomeric alkanes of the formula C5H12, identify the one that on photochemical chlorination yields a single monochloride to 3 isomeric monochlorides and 4 isomeric monochlorides. Now to write the various structures with the formula C5H12, so first of all write 5 carbon atoms in a chain. Then satisfy the remaining valencies of carbon with the hydrogen atoms. Now this carbon has a valency 1, so here you write 3 H atoms. This carbon has 2 valencies, so write CH2 here, so that the total valency is 4. Write CH2 here, write CH2 here, and then the carbon with 1 valency shown, write CH3 there. And this is called normal pentane or pentane. So we have written 5 carbon atoms in a chain. Now for the second isomer, you write 4 carbon atoms in a chain. Now there is 1 carbon remaining. If we connect the 5th carbon to the end carbons, these 2 carbons, then we get N-pentane. So you avoid these 2 carbons. Then you can connect the 5th carbon here or here. If the 5th carbon is connected here, and if you are numbering the chain 1, 2, 3, 4, then the branch or substituent is on carbon 2. If you are connecting this carbon here, then you number it from starting from this point 1, 2. So again we get the branch on carbon 2. So connecting the 5th carbon here or here gives the same isomer. Now you satisfy the valencies. CH3, 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 CH2. Now here 1, 2, 3 valencies are there, so you write CH here. Now this is called 2-methyl butane. Because the longest chain contains 4 carbon atoms and hence the parent is butane. There's a branch on carbon 2, hence 2-methyl butane, or it's also called isopentane. Isopentane. Now, initially we started with the 5 carbon atoms in a chain, and then we started with the 4 carbon atoms in a chain. Now we start with the 3 carbon atoms in a chain. Now 2 carbons are remaining. If you connect the 4th carbon here and the 5th carbon here, we get N-pentane. So we can avoid these 2 carbons. And again, if you connect the 4th and the 5th carbons here, we get this structure. So that possibility is also avoided. So the only remaining carbon is this middle carbon. You connect the 4th and the 5th carbons to the middle carbon. Then you get CH3 here, CH3 here, CH3 here, and there is no H on this carbon because already its valence is 4. So CH3 here. Now this molecule is called neopentane, or we can call it two dimethyl propane. Now consider N-pentane. You place a mirror at the middle carbon, then these two groups are coming as object and image structures, and so we can say the methyl groups are similarly placed and the CS2 groups are similarly placed, and this CS2 group is unique. So we can have one chlorine here, that is CS2 Cl CS2 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 CH3. So place the mirror here. Then this is a different carbon, so you connect Cl there, CS3 CH, you replace one H by Cl, then we have CS2 and CS3. Now this is one chloropentane and this is 2 chloropentane. Now this is different from these two carbons, so you connect chlorine here by replacing one H, so we get the third isomer. So N-pentane is the isomer which can give 3 isomeric monochloride. So answer to question number 2 is this one. So 3 isomeric monochlorides. Now consider the next isomer, that is isopentane. So CH3 CH2 CH CH3 and CH3. Now this angle is 109 degree 28 minutes. Now place a mirror on the dot line like this. Now you find this methyl and the methyl here are related as object and image groups. Hence these methyl groups are similarly placed this way. So these two methyls are similarly placed. So you show it by tick mark. Now this methyl is different from these two because this methyl is connected to a CS2, so this is different. Now this CS2 is also different because it is a secondary carbon, and this CH is different because it is a tertiary carbon. So we have now 4 different types of groups in this molecule. So this can give 4 isomeric monochlorides. You replace one hydrogen here or here by one Cl, then you get one isomer. So CH3 CS2 CH CS2 Cl and CS3. Now a second isomer is obtained by replacing the hydrogen here by chlorine. So we get a second isomer CS3 CS2 C Cl, CH3, CH3. Now if we number the structure, longest chain, this is 1, 2, 3 and 4. So this becomes 2-chloro-2-methyl butane. And this becomes 1, 2, 3, 4. So it is 1-chloro-2-methyl butane. 1-chloro-2-methyl butane. Now the third isomer is obtained by replacing one hydrogen on this carbon, and the fourth isomer is obtained by replacing one hydrogen on this carbon. So you can write the structures of the other two isomers. That is CS2, Cl, CS2, CH, CS3 and CS3. And the other isomer, last isomer is CS3, CH, Cl, CH, CH3 and CH3. Now numbering, the carbon connected to chlorine is given preference, so that this becomes carbon 1, this 2, 3 and 4. So it is 1-chloro-3-methyl butane. And this one is 1, 2, 3, 4. So 2-chloro, 3-methyl butane. Now consider the last isomer, that is neopenene. So the isomer which gives 4 isomeric monochlorides is started from isopentane or 2-methyl butane. Now the last isomer is neopentane. Now this is a molecular model of neopentane, where balls of different colors are selected but all are methyl groups, and these colors are selected because to introduce the symmetry of the molecule. Now consider a plane like this. Then this methyl and this methyl become images, so they are similarly placed. Now consider a plane like this. This methyl and this methyl are similarly placed. Consider a plane like this methyl and this methyl. This methyl and this methyl are similarly placed. So the yellow methyl and this pale rose methyl are similarly placed. They are related as object and image structures. Now consider a plane like this. Now on the other side we have the green methyl and the blue methyl, which are coming as object and image structures. So we can have different variations in which, say in this plane, the green methyl and the yellow methyl are similarly placed or are related as object and image structures. So all methyls are related as object and image structures. So we say this is a highly symmetric molecule. So all methyls are similarly placed in the sense that this molecule can have only one isomeric monohalogen compound. So if the halogen comes here by replacing hydrogen, or if the halogen comes here by replacing hydrogen, or if the halogen comes here by replacing hydrogen, and again if the halogen comes here by replacing hydrogen, all the monochloride derivatives are the same molecule. So we can write the structure of the monochloride derivative by choosing any one of the methyl groups. So here let us make this methyl, replacing one hydrogen by a chlorine, and CH3 here, and CH3 here, and CH3 here. So neopentane is the isomer which gives only one monochloro derivative, because neopentane is highly symmetrical. We can have a mirror plane like this, or a mirror plane like this. You place the mirror here, we get methyl and methyl as object and image. You place the mirror here, you get methyl and methyl as images. And again, by observing the model, we have seen that all methyls are similarly placed, so that there is only one monohalogen derivative. Now another question, that is this compound, an alcohol, and this is called cyclohexanol, reacting with SOCl2, that is thionyl chloride. The OH is being replaced by chlorine, sulfur dioxide is a gas, HCl is a gas. Now briefly the mechanism. First of all, the OH reacting with the Cl of SOCl2. SOCl2 is S double bond O, bond Cl and bond Cl. So HCl is removed, O getting connected to sulfur, O, S double bond O, Cl. Then I told you an SN I reaction occurs, substitution nucleophilic internal reaction, where this bond connected to O migrates to the position in between S and O, and to maintain the valency, this bond will be migrating in this direction, so that the bond along with chlorine will be connected to this position. So we get Cl here and SO2 as a gas, sulfur dioxide gas is produced. Now another compound, that is para-nitro ethyl benzene. Now this nitro group has nothing to do with the reaction when it is treated with the bromine in presence of UV light or heat. It is a free radical reaction, and again a secondary free radical is more stable than a primary free radical. So a secondary free radical is formed during the reaction mainly. Now here first of all a brief survey of the mechanism. Br-Br bond undergoes homolysis giving two Br free radicals. I told you a free radical is a species with a unpaired electron, and it is highly energetic because the energy given for supplied for homolysis is taken up by the radical, so it is in a high energy condition that will be reacting with this para-nitro ethyl benzene. Now the CH bond undergoes homolysis. This carbon gets an unpaired electron, hydrogen getting unpaired electron. So this hydrogen with its unpaired electron will form a sigma bond with the bromine radical, producing HBr, and a radical center is created here. Now this radical center is stabilized by hyperconjugation. Now this half-a arrow indicates that only one electron is being given to this carbon, and the electron on this carbon combines with the electron on this carbon. Now the orbitals are so placed that these two orbitals containing unpaired electrons are mutually parallel. We get a pi bond. Then this H as a free radical is remaining in close contact with this structure. So there are three CH bonds, hence three such hyperconjugation canonical structures are possible. Now again this radical center can be stabilized by resonance also, that is mesomeric effect. Now here the arrow starts from the pi bond. This may be considered as a pi bond. Now a half-cut arrow indicates that one electron of this pi bond is given here for bond formation, so that one electron will be remaining here, so that electron is shown here. Now the orientation of the orbital containing single electron here and the orbital containing single electron here are mutually parallel, so that we get a pi bond. Now again there a half-cut arrow is shown that one electron of this pi bond, so we can consider this one as a pi bond, then it becomes a sigma bond. So one electron of this pi bond combines with this electron, unpaired electron orbital, and this unpaired electron orbital and the orbital here are oriented such that they are mutually parallel, so that the pi bond is formed here and the unpaired electron over this carbon connected to nitro group. Now then again half-cut arrow is shown, so that one electron here combines with this electron and the orbitals are oriented such that they are parallel. We get a pi bond, and unpaired electron is here. Now the half-cut arrow indicates that one electron of the pi bond here combines with this pi bond, combines with this unpaired electron orbital, and these two orbitals are mutually parallel, so we get a pi bond here. So the radical center radical can be stabilized by mesomeric effect also, so there is higher stabilization of this secondary radicals, and hence the product is formed. Now coming to this compound, that is para-hydroxybenzyl alcohol it is called. So it is a phenolic derivative because phenol is C6H5OH. So when OH group is directly bonded to the benzene ring, we call the compound as phenol. Now here there are two OH groups. One is a phenolic OH group and the other we can call an alcoholic OH group. Only alcoholic OH group will react with the HCl in presence of anhydrous zinc chloride, removing HOH as water, and then CS2 is getting connected to Cl. Now why this OH is not replaced by chlorine? And that is because the lone pair of oxygen undergoes resonance with the benzene ring. So that is a plus M effect. So phenol shows plus M effect. Now for this lone pair to become a bond pair here, this electron pair has to migrate in this direction. Then this carbon is left with a vacant orbital and a positive charge. Now this lone pair orbital, the oxygen atom will change its hybridization from sp3 to sp2, so that we get a p orbital containing a pair of electrons that will overlap with the vacant p orbital created by the polarization here. Now a bond will be formed. Since oxygen atom contain a lone pair and this carbon contain a vacant orbital, one electron will be given to this carbon, so that its positive charge obtained by removal of this pair of electron is neutralized, and oxygen carries a positive charge here. So it becomes a double bond, and here we get the pair of electrons in the pi bond as a lone pair. Now there is further resonance occurring here. Now this bond, the pi bond, will be shifting over this carbon. In the sense, the pi electron pair goes entirely into the orbital of this carbon. Now this pi electron pair will be forming a bond here. So when this electron pair is forming a bond here and this electron pair shifts, this orbital created here, a p orbital, will contain a pair of electron and a bond is formed here. And when this electron pair moves in this direction, this carbon gains a positive charge and a vacant orbital. Now this electron pair in a p orbital, these two orbitals are mutually parallel. The vacant orbital here formed by this shift of electron pair, and this lone pair orbital, they are mutually parallel and they overlap to get a pi bond here. Now one electron is given to this vacant orbital during this bond formation, so this negative charge is getting neutralized, and the negative charge will be observed here because this shift creates a pair of electron in the orbital of carbon. So that now this will continue, and this lone pair becomes a bond pair here, and this bond pair becomes a lone pair here. So we get this structure. Now again, this lone pair can become a bond pair here, and this bond pair becomes a lone pair here, and we get the final structures. Now the sum of these canonical structures, some of the characters of these canonical structures is that the oxygen atom of phenolic OH group is bonded to the benzene ring by double bond here, double bond here, and double bond here. So CO bond here will be having double bond character, and a double bond is a stronger bond than a single bond. So it is difficult to remove such an OH group which is connected by a double bond to the benzene ring. So it is difficult, not easy. So the usual reaction of alcohols cannot be given by phenol. So the OH group cannot be replaced by Cl, and this is due to the double bond character, and this double bond character is entirely due to what is called resonance. So resonance is the answer of most of the questions, theoretical questions in organic chemistry, and hence the CS2OH group will be substituted by chlorine. So we get para-hydroxybenzyl chloride. This is para-hydroxybenzyl alcohol, and the product is para-hydroxybenzyl chloride. And you need not remember the names but understand the reaction.